there was an old, very difficult problem about the relationship between consciousness and physics, right? The mind, you can think of the mind-body problem that way. And I think, my own view, we can go into this later if people want to, that actually is perhaps the most intractable looking problem that we have. And then Professor Malatesti's talk was pointing out some other things that might look a little stranger, that you say, well, gee, you think maybe there's a problem about consciousness and physics, but don't we at least know that biology reduces in some sense to chemistry, which reduces in some sense to physics? And then part of his claim was, no, there's actually problems even just with chemistry to physics. And then the suggestion was made from the audience that there's problems of reducing solid state physics to fundamental physics, so there's not even a clear relation of physics to physics. And I think that's a different kind of problem, and I want to talk about why it seems to exist and why it shouldn't exist. And maybe by the end it will be, I hope, clear why, if those seem to be problems not to me of reduction, but problems with the understanding of fundamental physics, right? The state of fundamental physics. And then if we clear that up, at least chemistry and biology and everything else should follow along just fine, at least in principle, and we would still have the mind-body problem in the sense of consciousness. It wouldn't be touched by all of that, which I know. But and another way to sort of to maybe set this is to say, if in the back of your mind you think there really is this fundamental problem of relating physics to consciousness, and you think experience is a form of consciousness, then you're going to say, gee, there's a fundamental problem relating physics to experience, but then how do we understand physics as an empirical discipline? Because it seems as though if there's no relation between physical descriptions of systems and experience, how can we use experience as, in some sense, a standard against which to hold physics? All right. Now, I think all of this traces back to just fundamental problems in understanding physics, and that's basically what I want to talk about, in the case, particularly in the case of quantum physics. So, metaphysics, sort of fancy-sounding term. And I just want to let people, don't worry about it being fancy. It's actually very simple. All I'm asking about is, when you're doing quantum mechanics or quantum physics, what is the basic ontology of the theory? That is, what is it that your physical theory, as a physical theory, postulates to exist? John Bell, who is, I think, the deepest thinker about this sort of thing in the last half of the last century, introduced the term beables. I don't know if he was probably aware that he was just reproducing the etymology of ontology. He didn't like, for some reason, he wanted to make up his own word. And he talks about what a theory says there is. And so when we're asking about what is the metaphysics of quantum theory, this is really a question about physics, understanding it as a physical theory, which is what is it that this theory is postulating for there to be. Now, you might say, okay, why don't I just pick up a physics book? Why don't I just pick up my introductory quantum mechanics book and read the first page and find out? And what you find when you open up that book is a very clearly defined mathematical formalism on the one hand, and on the other hand, a set of rules which in certain ways are not precisely defined about how to use that formalism to make certain predictions. But what you don't get is any clear account of the ontology of the theory, what the theory actually says there is. And so it might raise the question, how did that happen? Because this has not traditionally been the way physics works. And when I say it's not traditionally been the way physics works, you might take as a nice example, and we'll talk about this a little more later, if you open up Newton's Principia, he's very clear in the opening pages of that about the new notions he's defining and the status of particularly space and time that he is using to formulate his physics. So whether you agree with it or disagree with it, at the end of the day, if you just read the beginning of the Principia, you understand more or less, at least at a certain level, what Newton thinks there is. Now, I think philosophers have been somewhat complicit, maybe following along. I don't know if they were reading physicists more than following them, but they've been certainly complicit in allowing this sort of unclarity about the ontology of the theory to exist. So if we look back at a certain time in Ernst Nagel's book, which is really a classic book for the period, The Structure of Science, here's the way he characterizes a theory. So he says, for the purposes of analysis, it will be useful to distinguish three components of a theory. First, an abstract calculus, that's the logical skeleton of the explanatory system, and that implicitly defines the basic notions of the system. Notice it's an abstract calculus, we'll think what that means. Second, a set of rules that in effect assign an empirical content to the abstract calculus by relating it to the concrete materials of observation and experiment. And three, an interpretation or model of the abstract calculus, which supplies some flesh for the skeletal structure in terms of more or less visualizable materials. Now, in this three-part structure, if you're familiar with the history of quantum physics, particularly familiar with the way Bohr talked about what you had to do to, as it were, go from a classical understanding of the world to quantum mechanical understanding, you might think that, gee, 3 looks pretty detachable. If you think of it this way, you might say, well, maybe I just don't need 3. After all, what's it doing? It's letting me visualize things, right? It's making an anschaulich, right, literally picturable image of what's going on. And then Bohr can say, as a classical physicist, you expect this, or Nagel could say that, but you don't really need it. After all, if I throw that away, I've still got the logical structure, and I still can relate it to empirical observation. This is just, being old-fashioned, get with the program, toss it out, and then everything's okay. I think that's more or less the spirit that a lot of physicists approaches, and I've given this talk, and physicists have been nodding their head. Yeah, that's the way I think about things, too. I think it's a really terrible picture of the way a physical theory works. And let me say why. Obviously, he doesn't really talk about the ontology of the theory. I said, well, the ontology is tell me what the theory postulates to exist physically. What does he talk about? He talks about the skeleton of the theory, but that's not ontology because it's an abstract calculus, right? It's just a piece of mathematics. It doesn't say anything about the world. And if the abstract calculus doesn't say anything about the world, it can't be an implicit definition of any physical notion, right? Whatever he means by implicitly defined, that's also purely abstract. Okay? So this first part, part 1, contains 0 physics. So, how does this become an empirical theory if it has nothing in the first part? Well, that's why the second part is so important, because it has empirical content, it becomes empirically testable via the second component, which is this set of rules that assign some empirical content to the abstract calculus. In some places, these are called bridge laws, that in this history were supposed to be postulates which connect the unobservable or theoretical parts of the theory to the empirical phenomena. So you might imagine the general form being a kind of if-then statement. If, and now you have some statement in the abstract calculus, then, and you have some statement in the observation language. And if you have this kind of picture in place, then you can say, yeah, that fits what I just picked up in my quantum theory book. So here's an example. Again, this looks kind of technical, but don't worry about the details of it. But if you pick up a quantum theory book and you say, all right, there's a quantum theory of spin, and you'll be told, well, the spin of a particle, it's sort of like if you have a spinning top or a spinning ball, but then don't think it's like that at all, because it isn't like that at all. But it's sort of like that, but don't think it's like that. And then if you get to the brass tacks, you'll say, well, here's the abstract calculus. You have complex 2x1 matrices with 2 complex numbers, alpha and beta, and you require that it be normalized, so alpha squared plus beta squared equals 1. So that's just some mathematical set of mathematical objects. And then we have another set, the Hermitian 2x2 complex matrices, another set of complex numbers with certain features. And you can talk about these mathematical objects as forming a vector space, and the Hermitian operators are operators on the vector space. A hand in a vector, it's back another vector in a certain way. And you can define a bunch of just purely mathematical features of these mathematical objects. Okay, no physical content at all. And then you can say, all right, how do I make this into an empirical theory? I need rules. And the rules are going to look like this. When you prepare an electron in such and such a way, and now maybe you say you set up a magnetic field or you do something, then I will associate such an electron with this matrix, and when I prepare it in some other way, I'll associate it with this matrix. Okay? And when I do a certain sort of experiment on it, and I'll have to describe the experimental setup now. One kind of experiment I'll associate with this Hermitian matrix, and another I'll associate with this Hermitian matrix. And having done that, I now say, all right, here's how you use the theory. When the electron is prepared a certain way, now I associate it with this matrix, and now when I subject it to some experimental procedure that's associated with this other matrix, then I do some math and I say, okay, these things have certain eigenfunctions and eigenvalues and blah, blah, blah. This is all just mathematics. And I get some numbers out, and the numbers actually satisfy the axioms of the probability calculus we just heard about. And I say, so then I interpret these numbers that come out as the likelihood, the probability that you'll get this outcome as opposed to that outcome, or here are the number of possible outcomes, blah, blah, blah. Okay? And once you have those rules, you actually have an effective procedure, calculational procedure, which will allow you to make predictions about a certain class of experiments. Now I'm doing something I can test in the lab. And what's wrong with that as a picture of physics? Well, what I just said completely fails to provide any recognizable physical account of anything, right? I mean, I haven't, as it were, given you any physics. Why should I associate some matrix with a certain laboratory procedure? Why should I associate some other matrix with a certain sort of laboratory setup? What happens, if you're a physicist, you might say, look, what happens when the electron interacts with the experimental apparatus? Shouldn't I have a physical account of the interaction? Okay? What happens if I'm worried about something? And the other obvious issue about this is the way I've described it is that if I'm not performing a laboratory procedure on an electron, one of a rather delimited class of laboratory procedures. So one question is, why associate this laboratory procedure with this matrix, that laboratory procedure with that matrix? I have no explanation for that. But what if I'm not doing a laboratory procedure? What if I'm just worried about electrons that are in the sun? Okay? Presumably I should worry about electrons in the sun. They're important. But they're not being subject to any kind of laboratory procedures of any sort. Okay? So Bell, I don't know if I have it, Bell says, if you present it this way, it looks like physics is just about, right? Its content is about a very constricted set of operations you can carry out in a laboratory. And we thought physics was about the entire universe, most of which is not that. Okay? Now, how else could it work? I mean, if you read Nagel, you think, no, what they're doing is just what physics is. How else could physics gain empirical content? Well, let's look at what Newton does. Let's look at, in particular, Newtonian gravitational theory. What I'm going to say is sort of so obvious, but let's just work through it. Newton doesn't begin with an abstract calculus at all. Right? He begins by describing the structure of absolute space, time, and motion, which he says my theory is going to assume there's an absolute three-dimensional Euclidean space. There's absolute time that goes on. Things can change their positions in absolute space. That's their absolute motion. That defines an absolute velocity, acceleration, and so on. And then he says, and of objects, I'm going to say they have certain physical features like a mass. Okay, that's just a physical feature of an object, and there are these other things which are less familiar or less concrete, called forces in the world, but they have directions and magnitudes. So none of that, all of that is really ontology. And once he's set up, he can then say, okay, now, in terms of this ontology, I can give you some laws. And the main law is this one, that the total or net force on an object at any time is equal to its mass times its acceleration. He wouldn't write it that way. He didn't write it as an algebraic equation, but we can understand it this way. Okay? So that's now a law, physical law that relates physical quantities. Once you have that in place, then you can derive, by derive, notice this is not, as it were, an abstract calculation. It is determining what the physical postulates I just laid down imply about what things will do, right? I can derive what the motions of bodies will be in certain circumstances. If I postulate, for example, that there's this force of gravity that has, varies directly with the masses and inversely with the square of the distances, then I can derive the following claim. That if two bodies of different mass are released together at the same time above the surface of the Earth, with the only non-negligible force being that of gravity, which means basically the net force is just this gravitational force, then they should hit the ground at the same time. Right? And that's really a derivation. It just follows from my physical principles. If I let go of these two things and they're falling in a gravitational field, and the gravitational field is governed by this, and there are no other forces, they should fall together. They should accelerate together. One-step derivation, because m's cancel. Now, how does that give, now you might think, all right, let me go back. You might think, all right, now I have some empirical content I've derived from the theory. I mean, it's told me something observable. If you let go of, a big object and a little object off the leaning tower of Pisa, blah, 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 they'll fall together. But notice, in a certain sense, I haven't. Right? If you understand empirical content as having to do with the content of experience, and this again is bringing up a little bit the mind-body problem of consciousness, then Newton's theory hasn't been shown to have any empirical content at all. Right? Because nothing's been derived about anyone's experience of anything. All that's been derived is how, according to Newton's theory, bodies in certain physical circumstances will move. And it's obvious, in fact, that no claims about anyone's experience of anything follow from the whole of Newtonian mechanics, supplemented by what other force laws you care to postulate, right? You can make it as fancy as you like. You ain't going to get any derivable consequences about experience. However, what can you get? Well, given appropriate initial conditions specifying masses, positions, and velocities of the planets, together with the assumption that only gravity produces a non-negligible force, Newtonian theory will predict the orbits of the planets, and we can add geometrical optics, which is a claim that light moves in straight lines. The theory will predict the exact timing of eclipses, given initial data. And again, none of this makes any direct claim about anyone's experience of any things going on in the world. So then you ask, well, how is Newtonian mechanics an empirical theory if you can't derive anything about experience from it? Well, once you say it that way, it makes it sound like a great mystery, but it isn't. The answer is obvious, right? What Galileo, for example, simply reported the result of some experiments that he did, and he didn't report them in terms of his experience, he reported them in terms of what the bodies did, right? He reports that he let go of these different masses and he let them fall off a tower and they hit almost together within, 2 fingers breadth or something, and he says maybe there's air resistance, blah, blah, blah. Okay? That's a report, not in terms of his experience, it's a report in terms of what some stuff did. Or you can compare the predictions of Newtonian gravitation to the observed periods, reported periods of planetary orbits, the times of eclipses, and so on. So the point is just that the language of the observational data, the language that's given to you as data, is the very same language that's found in the theory. It's a report of the relative motions and positions of bodies, macroscopic bodies. That's what you report. And if you do it that way, then this whole idea that you need some bridge laws or rules that somehow connect the observable part to the theoretical part just nowhere appears. You don't need any rules, right? Rather, the theory postulates laws for items moving in space-time, and the predictions of the theory are checked against reports of how things moved in space-time, or at least their relative motions. Again, Newton's very clear about this. What you can actually see are the relative motions, but of course, If the theory predicts the absolute motions, the relative motions are just the differences of the absolute motions, so the theory predicts the relative motions. Now, in this story, there's something very important, and this is what Bell called the local vehicles of a theory. So what Bell said is when you give me a physical theory, first of all, I want to know what are the vehicles. What does the theory postulate to exist? And in particular, what are the local vehicles? Among the things that postulate exist, some of them will be local. Here's what Bell has to say about the normal way you talk about quantum theory in terms of observables. An observable turns out to be a matrix, or it turns out to be an operator, something like that. Okay, so here's Bell. The concept of observable lends itself to very precise mathematics when it's identified with a self-adjoint operator, which is just a purely mathematical condition, right? But physically, what do you mean by an observable? Physically, it's a rather woolly concept. It's not easy to identify precisely which physical processes are to be given the status of observations and which are to be relegated to the limbo between one observation and another. So if you say, well, this matrix that is a mathematical thing I call an observable, it is applicable only when you make an observation, and then you ask, well, when is that? Right? What are the conditions under which an observation is made? And this was the part of the standard measurement problem in quantum theory, and I was just saying all of this is, as a physical level, very unclear. So here's how Bell thought you should make it clear. It could be hoped that some increase in precision might be possible by concentration on the beables, which can be described in classical terms because they are there. So by classical terms, he doesn't mean that they obey classical mechanics. He just means they are there. They're always there. At any given time, there's a fact about what they are. The beables must include the setting of switches and knobs on experimental equipment, the currents in coils, the readings of instruments. Observables must be made somehow out of beables. The theory of local beables should contain and give precise physical meaning to the algebra of local observables. So what Bell thinks is that an ontological postulate about what there is locally in the world, and locally means in a restricted region of space-time, is you appeal to that postulate to make sense out of the meaning of the abstract things called beables, which are just mathematical objects of a certain. And he goes through an example in trying to do this for quantum field theory. Now, quantum field theory has even extra confusions above regular old plain vanilla quantum mechanics. And Bell was trying to make sense of it. And some of this may seem a little technical, but it'll give you a flavor for what he was doing. So in quantum field theory, again, at an abstract level, you have a bunch of observables that are just mathematical objects. But he says they can't all be given beable status. They can't, each of these mathematical things can't correspond to something that's actually out in the world. Why not? Because they all don't have simultaneous eigenvalues. They don't commute. Now that's a mathematical condition, but basically it's saying if they don't commute, then you can't make sense out of postulating they're all actually there at the same time. They don't have the right mathematical features to have joint probability distributions. So it's important to realize, therefore, that most of these observables, right, these mathematical things, are entirely redundant. What's essential is to be able to define the positions of things, including the positions of pointers, or the modern equivalent of ink on computer output, right? Because if you get the ink on the computer output right, then you've gotten what we would say the result of the experiment right. I mean, ultimately, if you ask the experimentalist what happened in your lab, at the end of the day, he's going to hand you a sheet of paper with a bunch of ink on it. And if your theory can predict accurately the pattern of that ink, okay, it will have predicted accurately what we call the outcome of the observed outcome of the experiment. Yes? So the point of having the beables is that the theory predicts how the beables behave. If it predicts how the beables will behave, it'll make predictions that can be compared to the empirical data, what we call the data. Now, there are different possibilities for these beables in quantum field theory. Bell said, you look at quantum theory, you knew the theory abstractly, mathematically, as well as anybody in the world. But he said, you can't look at it abstractly and mathematically and decide what the beables are. So he went through some examples and settled on some, and he could have chosen other ones. I mean, it's left open by the math what you do here. So in making precise the notions of positions of things, the energy density, so this is if you know your relativity, the 0, 0 part of the stress energy tensor, it doesn't matter, comes immediately to mind. This is what you might think of as a thing you want always to exist with a definite value. At any point, the x would be at every point in space. This thing has a definite value, right? That would be making it into a beable, always there. However, the commutator, and this is, as it were, the energy density at the point x and the energy density at some other point y, their commutator is not 0, but proportional derivatives of delta functions. Okay, that's fancy mathematics. So they don't have simultaneous eigenvalues for all of x, and so we would have to devise a new way of specifying a joint probability distribution. This just mathematically doesn't look like a good choice for something to represent what's always actually there. So we fall back, he says, on the second choice fermion number density. Your fermions are like your electrons and your quarks. So the basic idea is if you can tell me at every point in this room what the density of fermions is, how many electrons and protons and neutrons there are, you can reconstruct what's going on in this room, right? I mean, if you told me through all time, well, you could see that I was waving my hands around and, somebody's going like this and somebody's going like this. And all, the sound waves and all that stuff would clearly be, all of that, what we think of physical conditions here, would be contained in that information. So we fall on the second choice fermion number density. The distribution of fermion number in the world certainly includes the position of instruments, instrument pointers, ink on paper, and much, much more. If you nail that down at all times, you've nailed down a perfectly adequate, at a microscopic level, a perfectly adequate account of what's going on in the world to correspond to what we think of as our experience. Notice, it's not, he doesn't get these things but from the wave function. So what we normally talk about in quantum theory is the wave function, and what follows from the wave function. But Bell isn't talking about the wave function. He's holding fixed. In his theory, the way you deal with the wave function in quantum field theory is just the way you do it in any standard textbook. He holds that fixed and its dynamics fixed. It's governed by some equation. But none of that, what's going on with the wave function dictates in any way at all what the local variables of the theory are. Right? What's going on in any particular region of space-time. Indeed, there are different physical theories that can be constructed that employ this abstract quantum formalism. And the first thing you need to do to understand these different theories, and these are actually different physical theories that go by, unfortunately, the bad name, different interpretations of quantum mechanics. As if quantum mechanics was a physical theory, and then somehow interpreting it is adding on to that physical theory some extra, I don't know, philosophical coloring that's supposed to make you happy. No, there is no such thing as quantum theory, as a physical theory. There's a quantum formalism. And what you're doing when you postulate different local variables is constructing physically different theories that happen to use the same mathematical formalism. Okay? And the point here is that if you want to ask, how does this theory make contact with data, and therefore contact with what we think of as empirical input, you need to first ask the question, what are the local variables in it? What is there in this, what, according to this theory, is there in small localized regions of space and time? Now, the same issues arise for non-relativistic. Bell was doing it for quantum field theory, but in regular non-relativistic quantum mechanics, you have exactly the same problems. Even if you give me a wave function and a dynamics for the wave function, there are still many different distinct physical theories that are possible. And the first question you want to ask yourself in trying to understand what is this theory telling me is what are those local things. Now, I'll just mention these. I'll give you a quick, if you're not familiar with them, because all of these are non-standard, right? So maybe the first point to make is, if you go into your standard physics book and open it up and ask, okay, here's your account of quantum mechanics. What are the local variables of this theory? You will not find an answer from beginning to end. Okay? There just isn't one. it's a very Hegelian. There's an apparatus and there's an association with certain procedures and blah, blah, blah. But if you ask, no, don't tell me about that. Tell me in a hydrogen atom, okay, what's there all the time? You won't get an answer. I was just reading a book by Sean Carroll, and Sean, when he's trying to describe quantum mechanics in this book, it's a book about the Higgs boson. And he says, online, he asked people to give the best 5-word summary of quantum mechanics. 5 words. And of all the things, the one he chose he thought was best was this. This is the way to understand quantum mechanics. Don't look waves, look particles. So Sean says, so what's that telling you? It's telling you that an electron, as long as you don't look at it, it's a wave. But as soon as you look at it, it becomes a particle, or presents itself as a particle. Now, if you think that's what's going on in the world, you're going to be really puzzled by what's so special about looking, right? I mean, that little 5-word summary tells you when you look at a system, you change its physical behavior in the most radical possible way. And people have said this, right? And that's why Einstein ends up asking, well, gee, who gets to look? Can a mouse look? You know, is a mouse a complex enough? Bell says, do you have to have a PhD to look? You know, if you think looking or observing or measuring has to play this absolutely fundamental central role in your physical account of the world, you better worry a heck of a lot about what the conditions for doing that are. And nobody has a theory of that. Nobody. Zero. Notice we haven't needed one. If you just have some local beables around that are always around, whether you look or don't look, and that are always following some physical laws, whether you look or don't look, and that your looking or not looking is itself just another physical interaction between things, which is what we think it is, then you don't have these problems. But you want to ask first, what are the local beables? Now, in standard quantum mechanics, you can answer that. Every answer gives rise to a theory that most physicists would say, oh, that's not a serious theory. That's just some crazy people think about that theory. But these are the only theories we have that actually make sense. These are the theories that Bell himself always tried to promote, to think about. And just, in case you're unfamiliar with it. Bohmian mechanics, a theory that goes back to 1927. De Broglie invents it, Bohm reinvents it, Bell pushes it very strongly. It says what there is locally are particles. And what I mean by a particle is what you always meant by a particle. A little, in fact point-like as far as you care, dot that's always somewhere and moves on a definite trajectory. Okay? And you and I and the table and everything else are just made up of these particles moving around and forming certain configurations. And what we want our theory to do is to tell us how the particles move. And we can compare the predictions of the theory about how the particles move with what we see in the world. So in Bohmian mechanics, the local beables are point particles that just are always somewhere and have trajectories through space-time. There's another, in this theory, the wave function, and you'll notice I'm not talking about the wave function. The wave function is not a local beable. In this theory, the wave function never collapses. It always just evolves in a nice, smooth, continuous, deterministic way. Okay? What moves around are the particles. In some theories, the wave function collapses. The wave function sometimes evolves nice and smoothly and sometimes does something very different. And Girardi, Ramini, and Weber, these GRW guys, were the first ones to write down such a process as a clear, mathematically well-defined process and not a hand-wavy process. But in that theory, even though you have this funny behavior of the wave function, that still doesn't answer what are the local beables. And here there have been a couple answers. Bell suggested one, which is now known as flashy GRW. So just to give you a picture, in Bohm, if you looked in space-time at a fine level, you would see particles moving around, and it would leave little world lines like that. Okay? In flashy GRW, what there is locally in space-time are just points. Not points that persist through time, just points in space-time, events, dots. But you can imagine sort of filling up space-time with dots in the right way, that if you squint at it, you could sort of see, oh, there's a table here, there's a chair here. Okay? It would fill up certain regions of space-time, there'd be lots of dots, another region, a few dots. So this is flashy GRW. And there's another way of taking the same GRW wave function, this is now GRWM with a mass density, where what there is a kind of continuous matter field that can be denser and less dense in places. And you can imagine if you do that the right way, you might get something that looks like tables and chairs, right? Lots more density here than here and so on. Okay? All of these are consistent with the basic dynamics of the wave function, which is what the standard quantum theory gives you. Okay? And there are certain reasons to think this fits better with the math. I could go into that later, it doesn't really matter. But all of these are possibilities. These are theories you can understand. You can understand what you're doing, what the theory is postulating, how you analyze it, how you get results of experiments, predictions for experiments, and predictions for the sun, not an experimental apparatus, predictions of what the sun will do out of a theory like this. So this is really just like the same thing that happens with Newton, right? Because when I described Newtonian theory, I said, well, there's a theory, but actually it's not really, because you say, what is the local beables for Newton? Are they point particles? Are they sort of fat particles? Is there a continuous matter density? All of those could be treated using the resources of Newtonian gravitational theory. Okay? You could have continuous dust. They have different analytical problems. Each is a distinct physical theory. And Newton, of course, was agnostic about how the gravitational force among the massive objects was caused. So there's also a lot of fiddling that even Newton would expect would have to be done to his theory to fill it out to become a complete theory. No doubt there'd be some changes when you were doing that. But it's by filling in those details that you come to have a better and better well-defined actual complete physical theory. So to sum up this part, one part of the metaphysics of quantum theory ought to be telling me what are the local beables. Or else you have to give me a clear account of how a theory can have any empirical import at all without local beables, without there being anything going on in particular regions of space-time. And so here are some possible ways you could answer that question. And again, you won't find those in any standard physics book. If there are local beables, then we have no problem about what we think of the empirical consequences of the theory, because they're just a function of what it predicts about how the local stuff behaves, along with the assumption that, look, tables and chairs and ink and so on, basically they're made up of this local stuff. So you want to know what the ink is doing, you just follow it according to the theory and see what the theory says how it's going to behave. Okay? And you do that by analyzing the dynamical laws. Now, what about the wave function? Okay, so usually when you talk about quantum theory, everything's about the wave function. I didn't mention the wave function yet, right? Except tangentially. That's quite on purpose. Okay, so what can we say about the wave function? Okay, if we accept all this, then the first thing we learn is that whatever we say about the wave function, in some sense, it's a subsidiary or secondary element of the ontology. Why? It's not directly observable. Okay, what you directly observe, what the content of your observation reports are what happened to the local beables. The wave function, whatever it is, everyone will agree, is not a local beable. It doesn't have a value, as Bell would say. You can't ask and point at a point in space-time here, and say, what's the value of the wave function here? That makes no even mathematical sense. Okay, it's not defined on space-time. It doesn't have a local value. So, why think it exists? Why care about it? How does it have any empirical consequences? It has empirical consequences only insofar as it plays a role in determining the dynamics of the local beables. That's how you know it's there, or that's why you think it's there, because you postulate it as part of the explanation in writing down the laws for how the local beables behave, whatever they are. And so, now we need to make a distinction, and this is a distinction that often gets lost in the literature, between the mathematical object and the thing it's supposed to represent. So I want to just make a terminological distinction here between the wave function and the quantum state. Let me just make that distinction. So by the wave function of a system, I mean it's a mathematical object, right? It's an abstract object associated with the system in the calculational apparatus. Okay? The wave function is a function, and a function is a mathematical gadget, okay? So in the wave function, in the example of spin, the wave function was a vector in a two-dimensional complex vector space. You could use density matrices, and the wave function would be a 2x2 Hermitian matrix with unit trace. Fancy mathematical terminology, you don't care about that, it's just a piece of mathematics. In non-relativistic quantum mechanics, you use a square integral complex function on a high-dimensional mathematical space called the configuration space of the system. All that's important there is the configuration space is not itself physical space. Whatever it is, it's not physical, so mathematical space doesn't even look like this. What do I mean by the quantum state? With the quantum state, I mean whatever it is in the ontology of the theory, what the theory postulates as a physical reality, if anything, is represented by the wave function. So you have the normal relation between the representer and the represented thing, where the representer, in the case of mathematical physics, is a piece of mathematics, and the represented thing, we hope, is a piece of physics, right? It's supposed to be physical reality. The quantum state is not a mathematical entity, it's a physical entity. And what kind of a physical entity is it? Well, there are various questions we can ask about it, and these are basically asking what's the relation, the representational relation between wave functions and quantum states. We can ask, are there non-physical gauge, what are called gauge degrees of freedom, which means non-physical degrees of freedom in the wave function, the mathematical thing. What does that mean? Well, suppose I have two different mathematical gadgets, right? They're mathematically different. But given my understanding of the theory, they represent the very same physical condition. Then their mathematical differences don't correspond to any physical differences in the world. So those mathematical changes are not, are called gauge degrees of freedom. They don't represent real physical differences. So the one thing we'd like to ask, we have this mathematical gadget. We want to ask which degrees of freedom, which parts of it represent physical facts and which don't. We can go back to these spinners. Generally, it's agreed that some of the degrees of freedom, mathematical degrees of freedom, are merely gauge. They're not real physical degrees of freedom. For example, an example of one of these spinners would just be, 1 over root 2. Well, doesn't even matter. Let me just do that. 1, 0. Okay, that guy's okay because this squared plus that squared is 1. Now I could change that to put a -1 there, for example. This corresponds to multiplying this whole thing out front by -1. Or I could change this to an I, right? I0. That corresponds to multiplying the whole thing by I. In the standard theory, all of these represent the same spinor state, right? These either mathematically different, obviously. But any physicist would tell you, no, these are just, there's no real physical, there's no physical choice whether this is right or this is right or this is right. If it's okay to represent a particular system with this, it's equally as good to represent it with this. It's equally good to represent it as this. So the overall phase, what we call the overall phase, this e to the I theta out front, is considered a gauge degree of freedom. It doesn't really mean anything. Further, you can go further and say even the magnitude, you can have a theory where I can multiply this by 2, right? So I could do that and say even that represents the same physical state, right? If you think of that as an equivalence relation. And that corresponds to saying that really the physical state is represented by a vector in Hilbert space. These are not questions you can answer by mathematical analysis, because it's a question of how the mathematics plays into the physics. If we accept this, in the representational relation between wave functions and quantum states is many one, right? Many different wave functions can represent have the same physical content. So we want to get clear about that. There are deeper questions. There's general agreement about the gauge degrees of freedom in the wave function. There's little agreement at all about the basic status of the wave function as a representation. There's a deep disagreement about whether there's any quantum state at all. Is there, in a particular system, a particular single individual system in front of me, does it have a unique quantum state? We can, how am I doing on time?
15 minutes.
Oh, that's fine.
Is the slot, so if you could do it in the next 5 or
yeah, definitely. Okay, we can, if we're asking what is the relation between the wave function, this mathematical thing, and the actual state of individual systems, we have 3 main approaches to this. We can call it the statistical, the epistemic, and the realist stances about this. So in the statistical interpretation, the idea is that the wave function doesn't actually represent an individual system. It only represents an ensemble, a collection of systems. Okay? You can't ask of a single system by itself what its wave function is, but only of a whole bunch of them. Okay? And if that were true, then when the wave function behaves in a certain way, you might say, well, that's not so physically puzzling. For example, the wave function being spread out in space, on this theory, you say that doesn't mean that anything in an individual system is getting spread out in space. That just means that different elements of my ensemble are in different places of space. Okay? The ensemble's getting spread out by each individual one being in a different place. So that would then seem to say, okay, all this spreading of the wave function isn't so strange as it sounds. Similarly, the ensemble might not have a single value for a quantity, for example, the position of a particle, even though each individual particle has a definite position, because they have different positions. Okay? Why would you want to go statistical on the wave function? Well, the most prominent advocate of that was Einstein, for the obvious reason. He said, well, not the obvious, he gave an argument, he, Podolsky, and Rosen gave us a famous argument that basically said, if the wave function isn't statistical in this way, if the wave function is a complete description of an individual system, not a collection of systems, then you get this spooky action at distance or telepathy, because when I have a system that has two parts that are spread out, part A and part B, and I perform an experiment on part A, the wave function of part B will change. And if you think this is a description of that particular system, it means that's a change in that particular part due to an experiment I did way over there. If you think it's just statistical, you might say it's not a big deal. All you're doing is changing the reference class when you make the experiment over here. You're resegregating it into a different ensemble. Okay? Now, what Bell showed, and this is why this is arguably the most important result in the history of physics, is that actually that's not going to work. That the EPR way of understanding this, it makes sense of the particular case they're worried about, but there are other predictions of quantum mechanics that you can't understand in that way without some kind of real physical non-locality in the theory. Why should you not go statistical? Well, think about why people thought this spreading out was something physical. Because you have interference effects, like in the two-slit experiment. You find that when you send a particle through two slits, as we have two open slits, it behaves differently than if either slit only alone is open. And that suggests that every individual particle that you send through is affected by the fact that both slits are open. So you don't want to think of the particle as somehow only interacting with one. So something seems to be spread out, even in individual systems. Something must be physically sensitive to the state of both slits along both arms of the interferometer in each individual experiment. So the spread outness of the quantum state, as it isn't merely a matter of it being part of a collection. Now, there's a recent result by Pusey-Baer and Rudolph. Here's the archive of the paper. And they gave a nice argument. I'm not going to go through it. Basically says you can't interpret the wave function statistically. If you try to do that, your theory will not make the same predictions as standard quantum mechanics. Okay, so this is sort of like a Bell result, and it's very pretty. If you're interested in this genre, it's read the paper. It's a nice pretty paper. If you think of the wave function as representing ensembles of systems, then ensembles. If you think that's right, then of course the same system can be associated with different wave functions, right? By being a member of different ensembles. And what they show is that that can't be right because those two different wave functions can't both make all the right predictions. So the wave function does represent something physical about each individual system after all. Okay? So that statistical interpretations are pretty much out. What about epistemic interpretations? Well, the epistemic interpretation is pretty close to the statistical interpretation. It says, look, the wave function doesn't represent any physical characteristic of the system. It just represents my knowledge of the system. It is the information that some person or cognizer has about the system. And since different people can have different information about the same system on this view, the same individual system can equally validly be associated with different wave functions, right? But that means it's going to fall, that position, this informational position, falls to the same argument, right? That is, The epistemic interpretation implies the same system can be equally validly represented by different wave functions in virtue of different people having different information about it. But the PPR theorem rules out epistemic interpretations just in the same way as it does these statistical interpretations. The wave function is a feature of an individual system and not our knowledge of it. And so we're left with realist interpretations, okay? There's some real physical characteristic of individual systems that's represented by the wave function. Now, even among the realism, there are different varieties. Okay, there is a quantum state, a physical characteristic that plays a role in determining behavior of the system, in particular the local variables of the system. But we can distinguish those positions. According to some, the quantum state is complete, and in some, it's incomplete. So this is the very first cut you want to make in making a distinction among realists about the wave function. What does that mean? Well, if the wave function is complete, it means that if you tell me the wave function of a system, every other physical feature follows from that. Right? It's somehow informationally contained in the wave function. Same wave function, same everything. It's kind of a supervenience thesis. In particular, if there are local variables in this sort of theory, their state is determined by the quantum state. This is true in this theory I call GRWM, GRW with a mass distribution. This mass distribution that I drew on the board actually is derived from the wave function. Right? What its density is a mathematical function of the wave function. So you tell me the wave function and how the wave function is changing. I'll tell you how this mass density is changing. Now, the way you go from the wave function, which is a complex function on configuration space, down to this thing, which is just a regular scalar density in physical space, it's not trivial, and there are different ways to do it, and you want to think about those. So in this picture, the quantum state evolves. As the quantum state evolves, the local variables evolve in space-time, and so the behavior of the local variables predicted by the theory can be compared to empirical data. On a picture like this, it's essential the quantum state evolve in time. Right? It has to evolve in time because we think local variables evolve in time. And on this picture, if the quantum state didn't evolve in time, all of physical reality would be static. Okay? And that doesn't correspond to the data. On a picture like this, there's really just one real quantum state. It's the state of the whole universe. It directly determines how all the local variables behave. In the flash ontology, it's sort of similar, only basically what these flashes represent are the centers of collapses in a collapse theory. So there are these dots. It's important that the wave function collapse, or there wouldn't be any local dots. Bell originally proposed the flash ontology. It's been developed by Roddy Kamolka into a fully relativistic version of GRW. And this is the same kind of thing. You see the wave function evolves, it collapses. Wherever it collapses, I put a dot in space-time. I then squint at the dots. That gives me a distribution of matter in space-time. I compare that to what I see. The other kind of picture is provided by Bohmian mechanics where the wave function is incomplete. That is, if you tell me the wave function, you don't tell me where all the local variables are. They could be anywhere, given the wave function. The role of the quantum state in this theory is to determine how the particles move, how they behave. And if they start in different places relative to a given wave function, they'll move in different ways. Okay? So the wave function here does not determine what the configuration of particles is, but it does determine how the configuration evolves through time. The quantum state in this theory is a variable. It's a real thing. It's not a local variable. It determines a velocity field on configuration space. And so there's really ultimately just one quantum state, which is the quantum state of the whole universe. Right? That's the only physically real one. And it's possible, notice, it's possible in this theory that the quantum state be static. It might never change. It's consistent with the quantum state in this theory, the universal quantum state being static, that still the particles move around. And you can ask how they move around, and whether they're moving around is more or less the way you think they move around when you look at them in the lab. So, different accounts of the quantum state display different similarities to more familiar physical posits. I'm almost at the end. If the universal quantum state evolves, changes through time, that reminds us a bit of a classical field like the electromagnetic field, even though it's not a local variable in physical space-time. And if the universal quantum state is static, it reminds us rather of a law of physics, like Maxwell's law of electrodynamics, that determines the dynamics of a local variable. In the end, these analogies are no more than that. The quantum state, I think, so sometimes people ask, well, quantum state, what is it? Is it a property? Is it a law? Is it a blah? My answer is the quantum state, right? We've no reason to think we come to physics preloaded with the right conceptual categories for what we're going to find. I think the right thing to say is, okay, there's a new physical category in this theory, quantum state. It's sort of like this, it's sort of like that, right? Don't expect it to be exactly like anything you were familiar with. It's an unfamiliar thing. So, in the final accounting, what is the metaphysics of quantum theory? Well, I haven't given you any particular answers, but I hope I've at least clarified what you're asking when you ask that question. If the theories have made contact with data, in anything like the way physical theories have through history, then there must be some local beables. There has to be something going on locally in space-time. The theory as it now exists gives us little guidance about what these may be. Theories using the abstract formalism with completely different local beables have been constructed and can be empirically adequate and can be tested. We have only slightly better luck with the significance of the wave function. There are plausible arguments the effect of the wave function should be interpreted realistically rather than statistically or epistemically. The mathematical object represents a real physical condition of individual systems, ultimately the real physical condition of the whole universe. But it's still open what the gauge degrees of freedom in the mathematical representation are and how the quantum state evolves. If it does, we don't even know that. So, this is one last quote from Bell. The kinematics of the quantum world, in this orthodox, what he calls he thinks the picture of Born, the Copenhagen interpretation, is given by a wave function, maybe more than one, not clear, for the quantum part, and classical variables, variables which have value for the classical part. So the whole state is a quantum state, psi, of somehow the microscopic bit, together with a classical state, and this is what Bohr always insisted on, there had to be a classical part of the description for the classical state. The big X's are somehow macroscopic. This is not spelled out very explicitly, right, by Bohr. The dynamics is not very precisely formulated either. It includes a Schrödinger equation for the quantum part, and some sort of classical mechanics for the classical part, and some sort of collapse recipes for their interaction, right? So this is the way, this is Bell trying to make sense of Bohr as clearly as he can. It seems to me that the only hope of precision with the dual kinematics, where there's both a wave function and something else, is to omit completely the shifty split between these two sides and let both psi and x refer to the world as a whole. So there's a psi for the entire universe, and there are these x's, these local beables for the entire universe. Then the x's must not be confined to some vague macroscopic scale, but must extend to all scales. In the picture of de Broglie and Bohm, every particle is attributed a position, x of t. Then instrument pointers, assemblies of particles, have positions, and experiments have results. The dynamics are given by the Schrödinger equation plus precise guiding equations prescribing how the x of t's move under the influence of psi. That's an against measurement. So, the extreme paucity of our results may come as a shock. The metaphysics of quantum physics contains almost nothing precise and detailed agreed upon at all. This is, though, the case with the metaphysics of Newtonian mechanics, as we've seen. Newton gave us a general framework within which detailed theories of point particles, extended particles, continuous matter, and so on could be developed. Similarly, there are various quantum theories that postulate different local beables, each of which must be evaluated on its own. There's a diversity of views about the quantum state. The dynamics of the quantum state can vary from theory to theory, as well as the way the quantum state influences the motions of local beables. And one little thing we know, but an important thing on account of Bell's theorem, is that there's some fundamental non-locality in the quantum that has no analog in classical theory. But beyond that, we must look to detailed theories, not to the abstract calculus they have in common, in virtue of which we call them quantum theories, for any guidance at all. And so now we can actually start. Okay, so this is now gotten us to the beginning of the discussion of what the metaphysics of quantum mechanics can be, particular detailed theories you can look at and analyze. I haven't talked about the many worlds picture, which is very much harder to understand, but if you want to, we can get to it. And that's the